Welcome! The objective of this video will be to learn how to classify functions around zero using Landaus big O symbol, and to operate with them, of course. We say big O as there is also a small o, but this is a topic for a different moment. So without further ado, let's start. We begin with an example. Observe the functions in the figures. On the left, we have the sine of x. On the right, we have 3x squared. Now let's look at these functions in absolute value near zero. We can see that near zero, both functions in absolute value are less than another function. In the case of the sine, in absolute value, it is less than the absolute value of x. On the right side, 3x squared is less than 3 times the absolute value of x. We will say that both functions are of order x near zero. Let's formalize the concept. Suppose that we have two functions, f and g, and let's compare them around zero. Choose the interval minus rr, any small interval around zero. If there is a finite positive constant m such that, in absolute value, f is less than or equal to m times g, then we say that f is big O of g, or that f is order of g as x approaches zero. We write, as you see, that f is equal to big O of g for x approaching zero. Be aware that this equal sign is not an equal sign in the sense of an identity, but it is in the sense of having the same order. Let's understand the definition by going back to our examples. In this first example, we have depicted the function sine of x. Now, we want to find a function g such that we can claim that the sine is order of g as x approaches zero. Checking the absolute value around x equal to zero, we can see, near x equal to zero, that the function absolute value of the sine of x is always smaller than the function absolute value of x. Again, on a small interval containing zero. Then we can say that the sine of x is order of x, or that the sine is big O of x as x approaches zero. Now let's change the function f of x to a function represented by a polynomial. In this case, f of x is 3 times x squared. We can see that f, in absolute value, is less than the absolute value of x on a certain interval. If we compute this interval, we can see that the 3 times x squared is order of x for x in the interval minus 1/3, 1/3. But we can also see that the absolute value of f is less than twice the absolute value of x, which gives that f is order of x for x in the interval minus 2/3, 2/3, or order of x for x in the interval minus 1, 1. This example shows that the interval minus rr and the constant m in our definition are related. In all three cases, though, 3x squared is of order x. Now that we understand the big O notation, let's see how we can work with it. The following properties will help us quickly simplify our operations. This theorem will show 4 basic properties for operating with orders. Let's understand them. Suppose that f is order of x to the p, and g is order of x to the q, as x approaches zero, and that p and q are non-negative numbers. Then, the first property states that f is of all non-negative orders less than or equal to p. Linearly combining f and g gives us a new function that is order of x to the minimum of the orders. Multiplying f and g gives us a new function that is order of x to the power the sum of p and q. And finally, if we divide f by x to the power t, the new function is of order x to the power p minus t, for t between 0 and p. Let's see the sum with one example. According to the previous theorem, if f of x is of order 2 and g of x is of order 3, then the sum should be of order 2, since 2 is the minimum exponent. Let's put numbers to the example. Let's take f of x to be x squared, which is of order 2, and g of x equal to x cubed, which is of order 3. Then, the sum is x squared plus x cubed, and it should be a function of order 2. Indeed, we can see that in absolute value, x squared plus x cubed is less than 2 times x squared. So this proves it for this particular example. Now, it is time for you to practice these properties. See ya!